Hello, welcome to this video. This is 7-5. We are talking differentiating logarithmic functions. And in this video, we're going to be working with a lot of logarithms and logarithmic properties. So make sure you are familiar and comfortable with logarithmic properties. And you can go back and watch 7-4 or go back and watch some of my accelerated math 3 videos on logarithmic properties just to help you gain familiarity there. Okay, so without further ado, let's go ahead and introduce the derivative of a logarithm. And what we're going to do is we're going to develop the derivative of a logarithm utilizing our definition of inverse functions. So if you can recall from 7-3, we have g prime of x is equal to 1 over f prime of g of x. Okay, and essentially remember, if functions are inverses, then their derivatives are reciprocals. Okay, so let us go ahead and identify that e to the power of x and the natural log of x, those are inverses, right? So they fit the case here, right, of f of x and g of x being inverse functions. So if I go ahead and I just say, okay, let f of x be e to the x, and let g of x equal the natural log of x, then I'm going to go ahead and substitute these into this formula here. Okay, so I want to go ahead and, right, in this video, we're developing the derivative of the natural log of x. So I take the derivative of the natural log of x. Well, this is going to be equal to g prime of x, right, which is the natural log of x. Okay, so that is equal to 1 over f prime of g of x, right? And we're getting that from here. So f prime of g of x. Well, g of x, again, is natural log of x. And f prime is the derivative of f of x. And what's the derivative of e to the x? It's e to the x. So I can go ahead and I can substitute in the derivative, right? So e to the power of x, right? And our input is the natural log of x. So we have 1 over e to the natural log of x. Well, e and natural logs, those are inverses. They can reduce, and we get the derivative of the natural log of x, which is 1 over x. So that is kind of the proof and how the derivative is developed. And here is the main formula that we're going to be utilizing. Now, oftentimes our problems will involve our inputs having another function. Okay, so we'll have to utilize our chain rule, right? So when we take the derivative of the natural log of a function, we'll get 1 over that function times whatever the derivative is of the inside. And we can go ahead and we can look at an example here. So y is equal to the natural log of 5x. Differentiate. Well, y prime is equal to, okay, so the derivative of a logarithm is, or a natural log, is 1 over whatever the inside is, 1 over 5x. Well, 5x is a function itself. I can take the derivative of that. So what's the derivative of 5x? Well, it is just 5. And if you want to go ahead and simplify this, you can. So it's 5 over 5x. Okay? And again, if you want to simplify, it would just be 1 over x, right? The 5s would reduce. Okay, let's look at number 2. F of t is equal to the natural log of 3t squared minus t. Okay, so I want f prime of t. So I'm taking the derivative of natural log, so it's 1 over the input, 3t squared minus t. Well, again, I have to take the derivative of the inside. So the derivative of that inside is, not 3, power rule, Schwarberg power rule, 6t minus 1. Okay, and again, if you want to simplify, 6t minus 1 over 3t squared minus t. So what I hope you're picking up on is that we put 1 over the inside, right? Whatever the inside is goes in the denominator, and then the derivative of the inside goes on top. And that is exactly what this kind of definition says, right? The derivative of the natural log of u is u prime over u. Okay, let's go ahead and look at another example. So h of x is equal to x natural log of x. Okay, well, in this case, we have a product rule. So we'll go ahead, we'll take the derivative of the first times the second, 1 times the natural log of x, plus the derivative of the second times the first. Well, the derivative of the second is 1 over x, and the first is just x, right? And this comes from x being what we call the first, right? And natural log being called the second. Just a little bit of review there for the product rule. Okay, and again, we can simplify this. 1 times the natural log of x is ln x. And then 1 over x times x is just 1. So there you have it. Okay, I know I didn't talk about these two formulas here, the derivative of log base a of x and the chain rule form, but we're gonna come back to those and we'll look at an example of that going forward. What we're gonna talk about right now is the natural log of absolute value of x. And over here it says, go ahead and graph this in the coordinate plane at the right. Well, maybe you're freaking out if you forget, but just remember, so with an absolute value of an x, you're going to go ahead and graph the right side. So remember, oh, hopped around here. Give me a second. Sorry about that. Okay, here we are. So we're going to go ahead and have an asymptote at x equals 0 and 0 at 1, and then the first point is over 2.7 up 1. So our function looks something like this. Okay, now remember with these transformations, since it's the absolute value of x, the left side goes away, right? Well, look at all of our negative domain values. There's nothing there anyway. And then all we do is just mirror it. So our function is going to be mirrored over here. So here's our graph, okay? And they say for the right half of the graph, the absolute value has no effect, okay? So for your domain values, x is greater than 0, your derivative is going to be 1 over x. Well, what about the left side? Well, on the left side, okay, if I go ahead and plot some slopes like they recommend here, plot some slopes. So I have 1 here, so at 1, you notice the derivative is 1. How do you know that, Schwarberg? Well, what's the derivative of the natural log of x? It's 1 over x, so 1 over 1 is 1. Okay, so I'm going to look at negative 1 on this side, and you'll notice the slope is exactly the same. It's just negative, right? It's decreasing rather than increasing. So if I go ahead and take that derivative, right? So again, the derivative is 1 over x. I know you're saying, Schwarberg, it's negative. Well, what is 1 over negative 1? Negative 1. So notice when we're differentiating the natural log function ln of absolute value of x and natural log of absolute value of u, the absolute value can be ignored. Does nothing, right? I just kind of wasted 3 minutes of your life to explain to you to ignore those. You're welcome. Okay, example 5. Find the derivative of the natural log of 5 minus 2y cubed. Sorry, the absolute value of that. I just kind of ignored that. I wonder why I did that. So it's going to be 1 over 5 minus 2y cubed times the derivative of the inside, which is negative 6y squared. Okay, and if you want to go ahead and simplify that, you can. I think it just makes it look a little bit cleaner. Negative 6y squared 5 minus 2y cubed. Okay. All right, now we're going to go ahead and look at a pretty gnarly logarithmic function here. And what we are recommended to do here is to simplify this logarithmic function. So notice here that we have a product rule going on in the numerator with a chain rule. We have a quotient rule, and that looks pretty ugly, right? Like, I won't touch that. So what I recommend doing is expanding it out using your logarithmic properties. And here's what we're going to do here. I'm going to utilize the quotient property first. Remember, if I have the same base, okay, we're dividing, I can go ahead and expand this out as subtraction. So I'm going to rewrite this as the natural log of x times the square root of 2x plus 1 minus the natural log of x squared plus 1. Now I'm going to go ahead and I'm going to expand my first term also, right? I'm multiplying, so I can go ahead and expand those as addition. So this is the natural log of x. You can use parentheses if you want, you don't have to. plus the natural log of, and I'm going to rewrite this like this, and you'll see why I'm doing this in a second, 2x plus 1 to the power of 1/2 minus the natural log of x squared plus 1. Now I'm not done. I'm going to go ahead and again, I'm going to rewrite this. I'm going to use the power property of logarithms, which says if you have an exponent in your argument, you can bring it down as a coefficient. So I have 1/2 natural log of 2x plus 1. And there you have it. Okay, so now I've expanded it. And I know you're saying, man, that took some math magic, but you're going to be very, very thankful, because what is the derivative of the natural log of x? Well, it's 1 over x. Y prime. I'll write it down here. Y prime is 1 over x plus, now I have 1/2 times the derivative of this, which is derivative of the top times whatever's on the inside, right? 2x plus 1. That's just the chain rule. Okay, 1 over x. And then minus over here. Again, I'll write it like this, right? So the inside goes on the bottom times the derivative of the top. And there you have it. That is your derivative. Not so bad, right? Okay. Last page. Example 7. Here is another proof, and this is going back to our first page to these definitions that I didn't touch on here. When we have a different base rather than base e, right? When we're not dealing with natural logs. So they say use the change of base formula to prove this or to show this. Well, if I have the derivative of log a times x, I can use the change of base, which says that I have natural log of x over the natural log of a. Okay, and I want to take the derivative of this, d dx. Okay, and I'm going to go ahead and expand this. So I want the derivative of 1 over the natural log of a times the natural log of x. And what I want you to think about is that the natural log of a is a numerical value. So that is a constant value, essentially. So remember, with constant values, you can just pull it out. So I can pull out the 1 over the natural log of a times the derivative of natural log of x. And what's the derivative of the natural log of x? 1 over x. So the derivative of this is 1 over x times 1 over the natural log of a, which, ta-da, gives us what we wanted to show. Okay, so essentially there is your formula. Again, you can thank me for wasting your time. Well, not really. If you're going to be a math major or you need those logic skills, or if you just care about where do these formulas come from, you'll thank me. So you're welcome. All right, example 8. This is the last one, and we're going to go ahead and use this formula that we just proved. So it says if y is equal to log base 2 of x squared plus 1, find y prime of 2. Okay, so I'm going to go ahead and take the derivative. So it's 1 over the inside, x squared plus 1, okay, times, again, the derivative of the inside goes on top. So I have 2x, okay, and notice this is not the natural log function. We're dealing with log base 2. So again, like our formula says here, we have to multiply by the natural log of the base. So multiply by the natural log of 2. And there is our derivative. This is y prime. Y prime. So we want y prime of 2. Okay, so y prime of 2, I'm going to go ahead and evaluate. This is 2 times 2 over 2 squared plus 1 times 1 over the natural log of 2. And you're done. If you cared about what it is simplified, this would be 4/5 times 1 over natural log of 2, which is 4 over 5 ln 2. All right, there you have it. That is differentiating natural logarithms and logarithms of different types of bases. Again, you need to be solid on your properties, so go back and view logarithmic properties if you need to. If not, catch you next time. Peace.